Welcome back. In this video, we will talk about the problem of finding a GCD or HCF of a number. What is GCD or HCF? It stands for greatest common divisor or highest common factor. Let's see what that is about. Basically, if the input is A is equal to 4 and B is equal to 6, what is the highest divisor that divides both of them? So in the case of 4 and 6, right? Of course, one divides A as well as B. But the question is highest one. How about 2? It divides both A and B. How about 3? No. How about 4? Yes, it divides A, but it doesn't divide 6. So it can go until the minimum of A and B, and whatever divides highest is the highest common divisor. In this case, it is 2. Okay. So let's take another example. A is equal to 200 and B is equal to 400. The minimum of this both is 200. And if you try to divide A by 200, it will give 1. Yeah, it divides. Similarly, B is divisible by 200. So the output is 200. For 9 and 10, only 1 divides both of them. If you try with 2, 3, 4, 5, 6, 7, 8, 9, nothing divides both of them, and hence the output is 1. So basically, if you provide any numbers that is a positive, definitely 1 is one of the greatest common divisors, but is it the greatest? That we need to figure it out. Okay, cool. So now that you have an idea of what this GCD is about, let's try to solve this using a naive solution. What is the expectation of this naive solution? You have a function GCD, and let's say we pass A and B, let's say to any two numbers. Now the idea is that you will find the minimum of these two numbers. Why are we finding the minimum of these two numbers? Highest GCD can be minimum of these two, right? It can't be like, for example, in the case of 4 and 6, it can't be 6. It can be only 4. So you can start from the minimum of A and B, and then you can decrement it and go till 1. So whenever you find the highest one, you just return it. Okay, great. So this is the idea. So please try to solve this in the coding exercise following. And if you already know the optimized solution, take it as an exercise and try to solve it. Okay, so we will see in the solution video. Thank you. Okay, welcome back. Hope you are able to solve the problem. In any case, let's go to the solution video. Great. So let me create a new file. So 05 gcd.js. Now let's create this function called gcd, and let's have two arguments, A and a B. Okay. Now as a first step, let's get the minimum value. So let result is equal to, how can we get the minimum of A and B? We can use the inbuilt math.min function. So A comma B. Now we have the minimum. So we can run a loop while result is greater than 1. Because when we have the 1, we should return it because that's the least GCD, right? So whenever the result is greater than 1, we say if A modulus result is equal to 0 and B modulus result is equal to 0, then what we will do? We will just return the result. If not, we will do result minus minus, and then at the end we will just return the result. Got it? So that's all the program is all about. So if you pass 4 and 6, minimum is 4, so it will start with 4. 4 is greater than 1. Whether A, which is 4%, 4 is equal to 0, yes, but 6% 4 is not equal to 0, so it decrements. It won't work for 3, but when it comes to 2, like this, both conditions are met, and hence we return the result. Got it? So let's add some test conditions. So console.log gcd of 4, 6. So let me copy this line and paste it a couple of more times. Second test case is 200, 400, which should give us 200, and then 9 and a 10. This should give us 1. Let's try running this. So node 05. Yep, As you see, you get output as 2, which is the expected one, 200, and then 1. Cool. So this is the naive solution. The next video, you will see a better solution. Thank you. Welcome back. Let's talk about the better solution. This better solution is based on a mathematical approach or algorithm called Euclidean algorithm. So what does this algorithm say? Let's understand. Let's assume for A and B, A is greater than B. Okay. Now, whenever B divides A, then we know definitely GCD is B, right? For example, in the case of 200 and 400, it assume like B is 200 and B is 200 and A is 400. In that case, B is dividing A, which means then GCD is B, which is 200. Correct? This is straightforward case. But we are interested in the case where this is not true. So what will happen in that case? Then A will be equal to Q times B plus R. What is that Q times B plus R, Harish? You're confusing me with this equation. A, we all know. Okay, let's take the example of 400 and 200. So now 400 is equal to, okay, maybe the better example would be like, let's take the example of 4 and 6. Okay, so in this case, A is 6 and B is 4. So 6 is equal to how many times B can divide A? It's 1 times, right? So Q is nothing but quotient. So 1 times B, which is then says 4 plus remainder. So what is the remainder? Remainder is 2, right? So because whenever you divide 6 by 4, it goes 1 times, which is the quotient, and the remainder is 2. So that's what this equation is all about. Now from this equation, what we can do is like we can get the remainder by doing A minus QB. We just send this QB to the left hand side. Okay, this is nothing different. Now, for example, let's say there is a common divisor for A and B, something called D. Then we can take D as a common and it will be something like A by D minus QB by D, right? So D is a common divisor for A and B. But what Euclidean algorithm says is that if it is common for A and B, this divisor, then this D is also a divisor of R, remainder. Okay. So this is all about Euclidean algorithm, which means what we can do is like whenever we are trying to find A comma B, we can just say GCD of B comma R. So we just pass B and then the remainder, because remainder is also a divisor. So by this way, what we are doing is like we are drastically reducing the one of the values, right? So it tries to reduce it to 0. We are trying to reducing it to 0. So probably I think this might be little confusing, but this is the mathematical proof. But let's see how this works in code. But if you understood, please try to solve this program on your own in the coding exercise. Also, to explain better why this is holding true, A comma B is equal to B comma R is, for example, let's take the example of GCD of 4 comma 6 itself. Okay, so 4 comma 6. Now I also said like this remainder is also a divisor, correct? Which means we are trying to, there is no need for this greater value, right? So we can just reduce it by calling, we will just pass the, I mean in this case it's 6 comma 4, sorry, 6 comma 4. Okay, then we will just pass 4 and then we will do A percentage B, which in this case is 6 percentage 4, which is 2. Okay, now when you try to do this again, you will pass B and then you will do A percentage B, which this time will give you 0. When this gets to 0, you just return this value. This is the GCD. That's all. So basically from A, B and R, we're just trying to choose the 2 minimum values. That's to be precise or concise, because A is 6, B is 4. We just need the GCD of B and remainder. So we are just trying to reduce it and reduce it until it gets to 0, and one value which is like A will not be 0, which is the GCD in our case. Okay, hope this helps. Try to solve it on your own, and we will see in the solution video. Thank you. Welcome back to this solution video. So let's see how to solve this using Euclidean approach. I'm going to show you two solutions. One is using recursive approach and another is using iterative approach. Okay, so let's start. Before starting, like the time complexity of this solution is theta of min of a comma b. Okay, whatever is minimum, and then it happens min times of a or b. Great. Anyway, so let's start with this another function GCD underscore EUC for Euclidean, and then we will pass a and b. Okay, now if you know what this Euclidean from the last video, what we need to do, we will just need to do return GCD underscore EUC of, okay, you will just pass b, and then we need to take the remainder, right? So a percentage b. But this is just not enough because we need a base case when we are doing a recursive function. So what we will do is like if you remember, always the b becomes 0. So b, whenever it is equal to 0, we will just return a, which is the GCD. Okay, let's try to copy this, and let's rename this, and probably I will comment this out so that it is clear. So let's try to run again. You see the output is the same. So in order to give you a clear picture of what's going on, so let's say we are doing a GCD of 10,15. Okay, I have always said that a has to be greater than b for this in the overview video of this solution, but it doesn't matter actually. Why is that? Whenever you do something like, see, in this case b is greater 10,15, what are we going to do in this case? We're just going to do b comma a percentage b, so which means b is 15, and then you will do a modulus b, which is 10 percentage 15, which will give 10. So it itself reverses it. Rather than you reversing it, it itself reverses it, and hence you need not worry about it. Okay, so it reverses it. Now the next condition is we will give the b and then 15 percentage 10, which is 5, and then 10 percentage 5 is 0. Correct? So now the b has become 0. We just return the a, which is the GCD. So this is how the solution works. Great. Now that you have seen this recursive approach, the time complexity of this is log of minimum of a or b. So basically it's actually logarithmic solution, log of minimum of a comma b. Okay, but the problem with this recursive approach is that it also takes the space of log of min of a comma b. So let's try to write an iterative solution which will take less space than recursive one. So let's try to do that. So function GCD underscore EUC for Euclidean, and let's say ITR for iterative, and then I will pass a and b. And now inside this we will do while b is not equal to 0, until this b becomes 0, we will do a is equal to a percentage b. We're just trying to do whatever we have done in the recursive to iterative. Okay, and now we have reduced the value of a, but then we need to swap those. So how can we swap those? We can use this latest features of JavaScript. So a comma b is equal to b comma a. So now b becomes a and a becomes b. Okay, now this will run until b becomes 0. So at the end we will just return a, which is our GCD. So let's try to run this using these test cases. So let me change the function names. Okay, if I try to run this now, it gives us the same output. Okay, so now you see this is the recursive way and this is the iterative way. The advantage with this iterative way is that it takes constant space or order of one space or big O of one space, but the time complexity remains the same, which is log of min of a comma b. Okay, great. How it is log of min of a comma b is outside the scope because it involves certain mathematical things. But in turn, if you see, this value gets drastically reduced, right? So it's something like dividing by 2. So that's why we say it's a logarithmic. Great. So see you in the next one.